Hey, it's me, it's your pocket tutor. And in this lesson we'll talk about forces. What are they, how we use them, and then we'll see some examples of those. So firstly, how are forces defined? Well, according to the classical definition, a force is a push or a pull that produces a change in an object velocity. And as we have seen in the last video, a force is a physical entity that can be described with a vector, since forces all have a direction, an orientation, and an intensity. This definition is kind of an abstract definition, it's not that easy to visualize, so it's much easier to think about a force effect. You can feel the effect of a force in everyday's life. Just think about these three simple examples that are gravity, friction, and spring. Just think about an object that is falling. What is pulling that object towards the ground is gravity. So we see the effect of a force, but we don't really see the force itself, right? Or think about rocks on the side of a mountain. Why aren't they just sliding off? Well, that's because of friction that is keeping them there. Or imagine that you are pulling a spring and it just tries to go back to its original position. That's the elastic force that the spring has. So you can actually see the effects of forces, but you cannot see them. But how can we measure forces? Well, we've seen in the first lesson that the unit of measurement of force is the Newton. As we've seen, Newton is a derived unit of measurement. And the instrument that we use to measure forces is the dynamometer. So the dynamometer is this instrument shown in the picture. It has a spring inside that we know all its properties, and then we have a small hook on the bottom. On the outside of the dynamometer, there is a graded scale that says how many Newton the dynamometer is feeling. But how can we space the different values of force? Well, 1 unit of Newton is given when we hang on the dynamometer 102 grams of mass. So, for every 102 grams of mass that we hang on the dynamometer, we mark 1 Newton. While would we, for example, hang 1,020 grams, so 1.02 kilograms, then we will just mark 10 newtons. And this is how we measure forces, how we can quantify them. But let's see some examples of forces. The first one and most simple one is the weight or gravity force that we feel on Earth. Now we have seen what's mass. Mass is defined as the amount of matter that a body has. And it's different from the weight, even though most of times we confuse the two terms. Weight is actually a force, is the gravity that we feel on Earth itself. So let's imagine that we go on the moon. Our mass wouldn't change on the moon, but our weight would change, since the gravitational pull of Earth is much different from the one that we would feel on the moon. In fact, the gravity that we would feel on the moon is 1/6 of the one that we feel on Earth. So if mass is quantified with the unit of measurement of kilograms, the weight is quantified in Newton. But how can we go from mass to weight? Well, there is a very simple equation. It is this one. So the weight of a body given its mass on Earth is given by g times m, where g is the Earth gravitational acceleration. Now the unit of measurement of the weight, as we've seen, is the Newton. The unit of measurement of g is meter over second to the second power. And the unit of measurement of mass is kilograms. And when you go back to the first lesson on units of measurement, you would actually see that we can go back from the derived unit of measurement of Newton to the ones of the international system. And you would actually see that the Newton is equivalent to this one, that is meter times kilograms over second to the second power. And this is the first actual important equation. It is the equation for the weight. And g is a constant. Well, g on Earth is a constant. Then on different planets we would have different values for g. But on Earth is equal to 9.81 meter over second to the second power. We've seen the other example of a very simple force that we will use later on in next videos. It is friction. Friction is a force that is always opposed to the movement of a body. We can distinguish two different types of friction. One is the static one, that is acting on a body when it's still. The other one is the dynamic one, that is acting on the body when it's moving. In order to compute the static friction, or Fs for static friction, we have this simple equation that is mu is the Greek letter that expresses the friction coefficient between the two bodies, times n, where n is the normal force. The normal force is the force that is acting on the body from the surface where it's standing in order to have an equilibrium, while the dynamic friction is basically the same. It's Fd for dynamic is equal to mu d, the dynamic friction coefficient, times n. Same thing, only the padding changes. Now, it's not really important where does this force come from. We'll see it much more in depth during the exercises that we'll see next video. The other force that we talked about that we're going to use it in the next videos is the elastic force. Now, the elastic force is also called Hooke's law and is written this way. Fe for elastic force is equal to minus k times delta, where k is the elastic constant of the spring. So this one is constant for a given spring. And its units of measurement is Newton over meter. While delta is the displacement of the spring itself. And its unit of measurement is, of course, meter. So in this picture that we can see, this one is delta. So delta is the difference between the final length of the spring after applying a force and the resting position of the spring itself. There's not much more to say about forces, but they are not as easy as they seem. We'll need to do a lot of exercises with them in order to understand them very well. So in summary, today we've seen forces, what they are, their definition. We know that they have a direction and an orientation, so we will need vectors in order to describe them. And then we've seen three simple examples that are the gravitational force or the weight that the body feels, whose equation is F is equal m times g, or g times m. The friction force, which equation is F for the static one, is mu s times n, the normal force. And lastly, we've seen the elastic force, that is F e equal to minus k times delta. Now, I haven't said that before, but the minus is very important, because if we apply a force to a spring, it will react always in the opposite direction of the one that we are applying to the spring itself. So be careful, this minus sign, it's very important. And this is it for today's lesson. In the next video, we'll do some exercises on these concepts and remember those equations. These are very important and we'll use them extensively. Bye bye.